Okay, welcome to class 2 of ETCS5201, Artificial Intelligence and Machine Learning 2. And today we're going to wade into some actual material. Today's material is going to be where we start down the path of looking at artificial intelligence from a neural processing perspective. So let's just kind of start digging into the material here. Now, here's an overview of what we're going to do. We're going to have this kind of introduction to neural networks, which is, as we're going to find out, a learning model that's inspired by biology. That's going to lead us to this kind of what's called the Perceptron model, which is kind of the really basic atomic level of neurological learning and simulation. We're going to look at, okay, now that we have that atomic level, what if we want to do more than that can offer? We're going to think, okay, well, we're going to need more than one neuron to do more complex things. But then we're going to go ahead and rewind back to that single perceptron because we really want to get a foundational understanding of how that works. We're going to then look in detail at how they learn. We're going to code one up. We're going to write some example code that builds our own perceptron, and then we're going to use it to solve some problems and look at some of the limitations that it has that are going to necessitate us moving to larger models or larger systems that have multiple neurons, essentially. Now, let's go ahead and kind of dig into this material a little bit further. So first thing is neural networks themselves, sometimes called artificial neural networks. They're a computational model that was inspired by biological systems, biological neural networks. So the question here is why? Why would we want to make a computer work like a biological system? And again, remember, this is an artificial intelligence class. So the idea was, well, we know that biological systems have been very successful in a lot of different ways. So rather than trying to reinvent the wheel, what if we just sort of, that is something that has proven successful. So let's maybe copy that and see what happens. And how successful has it been? Well, if you look at the tree of life that's depicted here in this image on the left, all the way back from the kind of first, they call it Luca, the last universal common ancestor back there, all the way through to humans, where I have that arrow pointing down there. And you can see all these branches. It's hard to argue the success of these biological systems, especially ones that have kind of neural network systems that allow them to react to their environment. So like even there, you got like fish going up to amphibians and reptiles and birds and mammals. And there's a large percentage of what's going on there that are these biological systems that have neural cells in them that allow them to react and adapt and learn and do things. And the idea with neural networks in artificial intelligence was, well, humans are in there, and we know that we think, or at least we claim that we think, and are intelligent. And so we consider ourselves to be truly intelligent in a general sense. So why not just copy what nature has already kind of figured out to make general intelligence, and we'll just duplicate what it does. So our brain, kind of this meat computer that we have in our heads, is filled with these cells that behave a certain way individually. And if you hook enough of them together in the right way, then you get get general intelligence that pops out of that, at least in the form of how humans work. So that was the motivation behind it, or what inspired us to do artificial neural networks, was to just duplicate what nature's already doing. And now the Uh, Biological systems evolved kind of populations of interconnected cells to get multicellular organisms. And some of those cells ended up as groups functioning together to exhibit complex behaviors, some of which are specialized, like organs, and some of which can adapt and learn and change their behavior over time. And you can kind of see that not just with our brains, but other parts of our, like your muscles. You work out, you get your body builds muscles. You learn new things. Your brain actually physically changes its structure as you learn information, and it grows different parts to cement those pathways in place. So the idea is that we can take inspiration of that and make systems that do a lot of those things by looking at how nature did that. And there are kind of two major subfields that are directly inspired by biological systems and processes that are at least two, but there are two main ones. One is what's called genetic algorithms, and the other one is artificial neural networks, or just neural networks. Now, genetic algorithms is something we're not going to spend time on this in this course. It's actually really fun to play with. It's a really interesting concept. So let's briefly talk about it. Unfortunately, we don't have enough time to do a lot of experimentation with that, although it is a really interesting and fun thing to experiment with. But genetic algorithms, the way those work is they take their inspiration not from like the neural cells and how those work in nature, but the very process that produced that tree of life to begin with. In other words, genetic algorithms, they the idea behind that is evolution by duplicating something that works very similarly to evolution by natural selection. So the idea there is we have a population of solutions, candidate solutions, that we evolve over time, over many generations, using principles that are very similar or analogous to how natural selection works in nature. We probably would call it more artificial selection than natural selection, because we're the ones choosing what to select for and what traits give the best results. We're defining that. But the idea is, while the genetic algorithms don't directly simulate or model at the cell level how biological systems work, it models the process of solutions being developed or found or evolved by selecting for traits among populations where we use randomness like mutation and recombination through reproduction, and then selection pressures. So the concept here is that you start off with this random candidate of a bunch of solutions. Most of them don't do anything useful, but some of them do a little bit of something useful. You take those ones and they survive to the next generation. You recombine them with each other. You add some mutations so they change a little bit, and then you do that process again. And then some of those do a little bit better, and some of them do terribly, and they get rid of the ones that, just like in nature, the things that do terrible at surviving die out. The things that do better at surviving live to reproduce. And then in the process of reproduction, there are some mutations that happen that changes them. There's recombination of the successful ones with the other successful ones via reproduction. And you eventually, over time, select for things that are highly successful. And when it turns out we can do that with solutions to problems as well. In fact, there are patents in the patent office that were invented by genetic algorithms. In other words, there are inventions, very complex inventions, that were invented through the process of, some of those are actually circuits, where the idea was, let's just make a whole bunch of random circuits that nobody designed or thought of designing or even had a concept. Throw a bunch of components together randomly, see what it does. The one that does better at what we want or the ones that do better at what we want, send them through the next generation, let them recombine parts of their circuits with parts of the other circuits that were successful, and then also mutate things, change add a resistor here, take a capacitor out there, move these around, swap these things. So just like what happens in nature, your genetic code, uh, your parents combine their two genetic codes to make this unique genetic code in you that gives you your own unique set of traits. But also then sometimes there are mutations that happen that out of the blue create some new piece of information. But over time and lots of generations and lots of populations, we get remarkably complex, uh, remarkably optimal solutions for things, where you end up with things like uh, house cats being like the ultimate like killing machine, uh, just because of something similar. But in genetic algorithms, we can, for example, use that same thing to design a solution to any kind of problem, as long as we know what traits we're selecting for. That's the major difference between genetic algorithms and natural selection, is we get to choose what we're selecting for. Now, contrasting that, notice this is not directly modeling the biological part of the system. If we contrast that, though, with artificial neural networks, the concept there is more inspired directly by the cells and the way that biological brains work at the kind of cellular level. So the idea there is we have specialized cells in our brains, and in the brains of any animal that has a brain, that's called a neuron. And that neuron has a particular way that it works, and it can learn and adapt and change itself based on input patterns and kind of a feedback mechanism that enforces some of the patterns and then de-emphasizes or reduces the importance of other ones. And so by that feedback mechanism that we call training, you end up with this neural mechanism that, because it gets rewarded, let's call it rewarded for good or positive outcomes, those get enhanced. And since it gets not rewarded, or we'll say punished, for things that lead to bad outcomes or non-optimal outcomes, it will lead to those being not favored in its behavior. So over time and over training, the system is going to kind of self-adjust and self-optimize to do things that because of that feedback mechanism, that maximize the reward and minimize the punishment. And we end up with now training these systems to do things. So it's a totally different way than you're used to with programming, where you think of the idea, put it into the computer, and now it's running your idea. Essentially, you're doing the hard work for it. In neural systems or in genetic algorithm systems, we're not doing that. In genetic algorithm systems, we're defining what we want and then using natural selection analogs and large populations of mutation to get that. In neural networks, we're creating a network model and then giving it data, telling it good job when it does a good job and saying bad when it does a bad thing. And that feedback loop in that network is over time going to optimize itself to do the things that we are training it to do. And training is the word we use. It's very much like how you train a dog. You say shake and it lifts up its paw, and you give your dog a treat. Works on most dogs. Does not work very well on Loki. He's very smart, but also very willful and stubborn. But the nice thing about these systems is that we don't have to come up with the solution. We train the solution. The bad thing about these is we don't come up with a solution. We try to train the solution, so we don't really, in a lot of cases, know exactly what it's doing or how it's doing it. It's a kind of you just train it and it just does it. And sometimes it fails and sometimes it works. And there's a lot of experimentation in this. And that's kind of one of the fun things about neural networks as well. We're kind of making these little brain kind of models and then teaching them things and then seeing what they do. It's a very explorative, very experiment-driven process that can be really rewarding and fun to play with. Now, as we said, the artificial neural networks being inspired by nature. In nature, they're all chemically driven. In other words, we have these cells that are chemically connected to other cells to form a network. And that network essentially has, like your eyes, photons hit cells in your eyes and they create this stimulus that fires nerves that go into your brain. It's chemical firing that goes into there, and your brain fires nerves that go into other parts of your brain and other parts, and then that's how you see things. And so the idea is that if you have enough of those and they're connected in the right way, they work to both sense things, like your sense of touch and smell and sight and sound. All of that is really those same kinds of neurons firing based on stimulus. And then they also work to process those messages in your brain itself, and then react and then produce an output that's complex, like you talking or you reacting and jumping away when something is thrown at you or whatever. You eating when you get hungry. All of those kinds of things are this chemically driven process that is done through these biological mechanisms. Now, in artificial neural networks, like we're going to be creating, the process is modeled as groups of simulated, interconnected artificial cells, and they still learn. They still interact with each other via interconnections. Those interconnections have weights associated with them and biases that are kind of the equivalent of how in biology there's a certain amount of chemical and a certain amount of connection strength with how much those are grown together and how they're configured with how they wire up to each other. The same thing is true in artificial neural networks, but it's done through these interconnections with weights and biases that are done mathematically to simulate what's happening chemically in the brain. Now, let's drill down in a little bit to what we're talking about with a biological neuron first, since that's what we're trying to simulate. So digging into the model of, this isn't even a model, this is actually how these cells work. The nature side of the equation, the biological side of this, is nature's neurons. And what those are is like a human neuron. It essentially is this specialized cell that has this, if you look over here on this kind of the left side of it, it's got these little kind of fibrous things that kind of reach out from the body of the cell, and those are called dendrites. The little channel pathways that come out of there that look like little tree branches, those are called dendritic branches. But essentially what those are the inputs that bring the chemical information, the nerve inputs. Those are the pathways that bring the input into the cell. And then that cell itself, kind of, you can think of it as gathering all of those inputs from those, or all of that chemical stimuli from all of those inputs, pulling them into the cell body. But then it has this specialized longer piece that goes across here. That's called the axon. And what that does is that connects to these other little branches over here, and those are called the synaptic terminals, or the teledendria, meaning tele at a distance, dendria. So they're kind of like these little dendrites here, but those are kind of the output of the cell. So the idea is all of those inputs from the dendrites get pulled in. They're kind of summed in the cell. In other words, they're all joined together into this one signal here that travels down the axon. And what the axon does is when the amount of that reaches a certain threshold, it fires the signal across that then gets branched out to these synaptic terminals that then connect to other cells. So this other green color over here is another cell that would have these coming into it, which then that would receive that and then repeat that, pull those in, fire that across its axon to another cell. And so we have this kind of network of gathering the inputs. If it reaches a certain threshold, it fires. When it fires, it goes to another cell, which gathers inputs, which reaches a threshold and fires, and so forth. So the idea is if the total of that input is greater than some threshold, it produces an output to the terminals, the synaptic terminals over here, which connect to other neurons. So not particularly complex. In other words, gathering inputs, summing them together. If it exceeds a threshold, fires an output, which goes through those little branches to other neurons. So if we break this down into the three major components, we've got inputs. Those are the on the left there, coming into the dendritic branches. All that gets pulled into the nucleus, which kind of sums it up. And then the axon processes the signal, including has that summation and the threshold. Actually, the summation happens more back in the cell, but then this has the threshold. It then causes that to, when it's exceeded, to fire. And when that fires, it goes to the outputs over here. So it has inputs, has a little bit of processing in the middle, and it has outputs on the other side. So not too complicated to model. Something that receives inputs, adds them together. If it goes above a threshold, it fires a set of outputs. Now, you would think with something so simple, how could we ever do something complex like have general intelligence? Well, it turns out that the human brain has 85 to 100 billion neurons in it. So really large amount of neurons in our brains. That's why our heads are so big. We've got a lot of meat computing to pack into there. And then the number of dendrites entering each neuron varies by which neuron it is and where it is and what type it is, but it could be no inputs to thousands coming in. So if you think about each one of those 85 to 100 billion neurons, each one could have up to thousands of inputs coming in and dozens or hundreds of outputs going out. That's a lot of connections and a lot of things going on in your brain. Now, your brain, however, does fire very slowly. It takes about 1/100th of a second to sum that up and then have a firing across there. Some cells a little faster than others, but somewhere around 1/100th of a second. So we're relatively slow processing speed-wise, but we have a lot going on at one time. In other words, it's like a storm. One fires, which goes to other ones, which go to other ones, and it just fires and ripples through that, like this lightning storm of fires. But the firing speed is relatively slow compared to how computers can do billions of operations in a second, like a typical modern computer, 4 gigahertz or so clock speed with multiple cores in there running simultaneously. Our brains fire about, instead of 4 billion times a second, about 100 times a second. But our architecture is a little bit different, that we're firing massive amounts of these simultaneously. A little more like a GPU, actually. But going back to that neuron model for a second. So that neuron model, we've got that kind of single neuron, dendrites on the left. The cell body there is kind of that orange circle over here in the middle area. And then the axon carries the signal across. When the threshold gets reached, goes to the synaptic terminals, in this case on the right. And if you follow the data flow there, the flow of information, you'll notice it has this nice linear flow from the dendrite inputs joined together at the nucleus, then passed through the axon threshold function or the impulse activation. When that gets reached, it fires across and goes to the synaptic outputs on the other side. So the data just flows through from left to right through that single neuron. Now, how can we model that in a relatively clean way in a simulated environment? Well, here's how that gets done. And you'll notice that it's really the same kind of model that we have. On the left, we have a collection of inputs. So in this case, I've labeled them x1, x2, all the way up to xn. That's like the dendrite inputs. That's the analog to those. And then, because each of those dendrite inputs on the biological version have different kind of thicknesses and different weights to them, they each bring a different percentage of the total amount in. We're simulating that with our model over here with these weights W1, W2, all the way up to Wn. In other words, each of the inputs gets multiplied by a weight that can either raise, or in other words, magnify, amplify the amount coming from that input, or push it down. And sometimes even push it all the way down to 0. Or you can even have weights that sometimes go negative to make that a negative input that comes into that function. So the idea is, think about those weights as a knob that we're turning the volume up or down of that input stimulus that's coming into that. Now, that next shape over there, that next box over where all that data flows into, this is essentially like our thing thumbing all of those inputs in the cell body that's going to then fire through the axon. But essentially what we're doing there, and don't get intimidated by the notation, that we're basically just saying sum up all of x sub I multiplied by w sub I. So we're just saying take the input, multiply it by the weight, add them all up. Super simple. We also have this plus b sub I that's adding what's called a bias. That takes, after we've made the whole sum, we can kind of shift it up or down a little bit, kind of like raise the whole thing. That's essentially like you can think of that as, after we've added it all together, we just want to maybe shift the whole thing up or down, which can help us achieve the threshold we're looking for that thing to fire. We don't necessarily want to multiply by the bias because we don't want to magnify it. We just want to have an offset. We're offsetting by the bias. And the bias could be positive or negative. It could be a negative number, which will pull it down, positive number, which will push us up. And then that gives us this value a sub I. That's the sum of each of the inputs times the weights, all added together, and then we add the bias to that. Now, from there, we pass that a sub I out, and that gets passed out to this, what's called the activation function. And what the activation function does is that's the thing that then, if a threshold is exceeded, or that's the thing that causes it to then fire across to our output here, Y. And then notice I have all these arrows coming out. That would connect potentially to other neurons somewhere. That would be the equivalent of our synaptic outputs on the cell. But in other words, we're gathering all these, weighting each of them individually, adding it all up, adjusting by the bias. If it exceeds a threshold or whatever our activation function is, there's different activation functions we'll look at later in the semester. But then if that gets exceeded, then that fires across here to go out to other uses, other connections on the output of that individual cell. And again, notice the flow left to right, and notice how much this very closely models the way the neuron works. Now, just walking through that model quickly here, you'll notice that how it works, all the inputs xi are multiplied by their weights. We kind of mentioned this on the last slide, but let's just walk through these bullet points. After those are multiplied, we just add them all together to produce the sum, a sub I. The sum, a sub I, then has a bias added to it. So b sub I is then added to that. That just translates that up or down. And then that gets passed into the activation function that determines the strength of the fired output y sub I. It might be it forces it all to 0, so nothing gets passed through. It might be that it amplifies it. It might be that it reduces it. But that activation function that happens inside of that circle, different activation functions produce different results. But that's all it's doing is determining the strength of how much of a sub I gets passed through to the output y sub I. Now, different activation functions produce different results or have different properties. And there's some common choices like just a simple threshold, a thing called ReLU, rectified linear is ReLU, hyperbolic tangent, sigmoid, softmax. We'll look at those later in the semester. But different functions have different properties. And it turns out the way biological things work, different nerve cells tend to activate in different ways as well. Now, that activated output yi basically just connects to the next neurons. And it might connect to one, it might connect to multiple things, or it might just be itself be an output node that says, this is my answer that I'm providing. Now, that single neuron by itself, we might think of as not particularly powerful because all it's doing is adding up the inputs after we weight them, adding a bias, and then running it through an activation function that gives us an output value. So very simple. Now, what makes neurological systems powerful, though, is when you have a collection of them in a group. And by having a group where one fires to one or more other ones, which fire to one or more other ones, and all of those each have their own weights and their own activation function and their own biases. And now if we train that, we can train it so we can get these complex behaviors, just like the human mind having 85 to 100 billion of these things all interconnected. And what that gives us the ability to have things that can be trained by adjusting those weights and biases through a training process. We can have something like, okay, the neuron in your toe, the nerve in your toe, when you stub your toe and hit it against the TV stand or whatever that you hit it against in the middle of the night when you're walking through your living room, that creates this impulse that then goes rippling through from your toe all the way up through your spinal column into your brain, and then through that neural network. And then your brain says, ouch, that hurt. And then presumably you get this negative feedback that tells you, don't do that again. So there's kind of this, ouch, don't do that again. That hurt. I don't want to do that again. That's a negative stimuli that teaches us not to do that. And you can kind of see that with kids when they're toddlers. They fall a lot, they cry, but they get better. And how are they getting better? What are they doing when they're falling and hurting themselves? They're training their neural network to walk better, to avoid hurting themselves. You don't touch things that hurt you. You don't do things that are, well, most people anyway, you don't do things that are going to be dangerous to you. And part of that is negative feedback from your parents teaching you. And part of it is the world teaching you not to do those things. You go to the playground and you jump off a thing that's too high. It makes your ankle sting. And you learn, maybe I shouldn't do that next time. Now, that's the basic idea with single neurons. But what I want to do is we talked about, well, back here a few slides, we said a single neuron itself is not very powerful. But I want to rewind to that single neuron a little bit, because it's misleading to think that a single neuron itself can't do anything. So let's rewind and talk about single neurons for a little bit. And a single neuron, at least in the simulated form of this, is called a perceptron. And what a perceptron is, you can think about that as the atomic level of neural processing. And it can't do a complex task like learn to juggle or learn to play Stairway to Heaven on the guitar, but it can still learn things and it can still adapt to situations. And even in their simplest form, the very simplest kind of perceptron we could make, in other words, we could take the simplest kind of neurological cell and boil it down to the simplest form of that simplest cell, and it can still learn or be trained to solve certain kinds of problems. So we want to go back and look at that and remind ourselves how it works, boil it down to its simplest form, and then we're going to look at the kinds of problems we can get that to solve. So here's a single perceptron in its simplest form. And this is that model we had earlier. This is what a perceptron is. And remember, as a reminder how this works, we are taking these inputs, multiplying them by the weights, adding them all up, adding a bias, feeding that in our activation function. That's giving us our outputs. Now, in the simplest form, we could get rid of a lot of those inputs and boil it down to, let's just say 2 inputs. We'll call them x1 and x2, which gives us then 2 weights, w1 and w2. And then we're going to multiply these 2 together, add those together, add the bias, feed that into our activation function. And our activation function, we're going to make that very simple threshold as well. And then that just feeds out to our output layer here, which is this yi layer. So that's in its simplest form. And so what we want to do is this simplest perceptron with just 2 inputs and 2 weights and this activation function, can we get this to solve a problem? Can we train it? Can we teach it to solve a problem? So what I want to do now is, let me describe the problem, and then we're going to see if we can get a perceptron that we can actually train to solve it. So here's the problem. Let's say since we have 2 inputs coming in on the left, let's treat those as xy points. So rather than x1 and y, or x2, let's treat them as x and y. Those are our coordinates of a point. And we want it to train this system to classify or sort the points into 2 different kind of groups. And we're going to call them like the red group of points and the blue group of points. And we want to see if we can train this where we don't have to tell it which group belongs to which class. We're going to teach it and have it figure it out on its own. Simplest kind of perceptron, single cell simulation with only 2 inputs, an X and a Y. And we want it to sort out, is it a red or is it a blue point? So here's the problem. We're going to feed in an XY coordinate as those 2 inputs, and we want it to output either one of 2 possibilities, either red or blue. So in other words, if I give it this collection of points and it sorted it, you notice all the red are kind of in the upper left, all the blue are in the lower right. And we don't want to write the code that just hard codes that. We want to have the perceptron learn through us training it. In other words, we're going to give it a point, and it might initially start out getting them wrong, and we're going to say, no, bad perceptron. And then it's going to, when it gets them right, we're going to say good perceptron. When it gets them wrong, we're going to say bad perceptron. And then over time, we're going to train it or teach it to do better. Again, kind of like your dog holds up its paw, you give it a treat, it learns that that's a good thing to do. You're reinforcing that. We're going to do that with this single cell thing and enforce its good behavior and kind of try to train out the bad behavior. And after we've trained it, what we'd like to have happen is now it can classify points it's never seen before. In other words, we'll give it a new point it's never seen before, and it'll put it in the right category with new novel data that it has not encountered before. So this is not memorizing. It's not going to memorize the list of good ones and list of bad ones. It's going to be learning the general trend of the red ones are up here and the blue ones are down there, and it's going to learn that. Now, here's our model. Instead of x1 and x2, we have x and y coming in. We still have our 2 weights, w1 and w2. And notice our formula is now simplified. I got rid of the summation symbol, and I just have x times w1 plus y times w2. You can see that in that box here. And then I just add the bias. And then here, I called that z instead of a subscript I. I'm just calling that z. So then I'm passing z to my activation function. And then I made my activation function, in this sense, we're trying to make this really, really, really simple. You'll notice that I made my activation function this simplest kind of form of this threshold that basically I said, hey, if z is larger than or equal to 0, I'm going to output a 1. If it's less than 0, In other words, if it's a negative number, I output a 0. If it's a positive number or 0, I output a 1. And so I have a little graph of that activation function that you can see up there above that box. Basically, it's a 0 until we hit 0, and then it jumps up to 1. It's just a step function that transitions at the 0 point. So it's, again, kind of like what we talked about in the biology. Once the sum is reached, once it becomes positive, it fires its value across to the prediction. And then my prediction, since I'm either firing a 0 or a 1, my prediction is, we're going to say 0 is blue, 1 is red. So that's my 2 points. So my prediction in this case is really just what I'm going to get out of this activation function is either going to be always a 1 or always a 0. I'm just going to say, let's arbitrarily say 0 is blue, 1 is red. So we've got two inputs, X and Y. We've got all of the data flow going through there, and at the end, it's going to report either a 0 or 1, a red or a blue. Now, when it gets it wrong, we need some way to teach it that it was wrong. And when it gets it right, we need some way to teach it it was right. So in our case, our inputs, X and Y, our outputs, either blue or red. And so the question here is like, how does it learn? How do we train it? How do we teach it? And it's not magic. It actually turns out the only knobs we have to play with here, if you look at that model, there are really only 3 knobs that we can tune to get this to do things. There's the weights, W1, W2, and then there's the bias. That's it. We can't even change anything in this model about the activation function. It's hard-coded. There's nothing in the prediction that we can change. It's either 1 or 0. So think about this as like a machine that has 3 dials that we can turn. We can increase or decrease weight 1. We can increase or decrease weight 2. Or we can change the bias, which raises the level after we do that, the multiplication and the sum either up or down. Just translates the whole thing up or down. Now, the question is, what sets those knobs? We could play with it ourselves and try to turn them and look at what happens. But we don't want to do that. We don't want to do a guess and check ourselves and use our brain to figure out. We want to train it to do that on its own. We want it to learn on its own. So here's how we're going to do that. We're going to train this by starting out with random weights and a random bias. We're just going to kind of pick random numbers and then see what it does. And then we're going to feed it data. And since it starts out with random weights and bias, it's certainly not going to work well as a classifier. It's just going to kind of do random garbage at the beginning. It's not going to have any idea what it's doing. But what's going to happen is sometimes we're going to give it a blue point, and it's going to say blue. And in that case, we want to say, hey, the weights that you had that did that, that was good. Let's do more of that. But sometimes when we give it a blue point, and a point in the blue region, it's going to say red, and we're going to say, hey, you did something bad. That was wrong. Let's do less of that. And so what we're going to do is we want to feed it data points that are already labeled that we know the answer to. Hey, these are red ones. These are blue. It's going to make a guess. When it guesses wrong, we're going to have an error term that we feed back in that says, that was wrong. Adjust your weights away from that. When it gets it right, we're going to say, good job, adjust your weights more toward that to do more of that. So in other words, what we're going to do over multiple training sessions and multiple data points is we're going to basically say, every time you get it right, we're going to move your knobs a little bit to make that, to enforce that. And every time you get it wrong, we're going to move the knobs away from that to do less of that. And over time, what we should see is rewarding it when it does good and punishing it when it does bad. I mean, rewarding and punishing are kind of these a little bit misleading. We're really just turning those knobs one direction or another independently. But what we're going to have over time is that this thing learns how to do this classification. And notice that we didn't have to do anything other than give it points we already knew the answer to, and then say good or bad, and it's going to learn on its own how to do the classification. Now, when we train it, we do have to give it labeled data though. And we're going to have to run that training data through multiple times. We can't just give it 1 point. It won't learn enough from that. So we might have to run through what are called epochs, which are multiple rounds of training. So in other words, you might say, hey, run through all these points and tell me how you did. And then we might look at how we're doing. It's like, let's try again. So in other words, just like with your dog, you don't just train it to shake once. You do sit today, and then you do sit tomorrow, and you give treats, and then you next week you do it again. And over time, your dog, or in this case, our Perceptron, is going to learn. Now, so here's our new model. When we make that prediction that comes out at the end here, we're going to say, if we know the truth, we're going to subtract the prediction from the truth, which basically means that if we're right, we have an error term of 0. And then that error term then will feed back in and adjust those weights and adjust the bias. So you notice I have the arrow pointing here at the bias and at the weights up here. And I also have this new thing here called the learning rate. And what the learning rate is that scales down our error term or up our error term. Think about that as the error or the learning rate as how much we're turning the knobs each time. And so in other words, you could turn the knobs very little each time, or you could turn them a lot each time. And it turns out the learning rate, if you set it too low, it'll be really stubborn. It'll take a long time for it to learn anything. It could never learn anything too if you set it low enough. In other words, if you have a learning rate of 0, it's never going to learn a thing. And if you set your learning rate too high and make adjustments that are too large to the knobs, you can kind of overshoot one way and then overshoot the other way, and you'll kind of never hone in on the actual best value. So there's going to be a little bit of experimentation with the learning rate to get that. We want to get a learning rate that kind of hones in on a nice optimal set of weights and biases without it taking too long and without overshooting or having things that diverge at the end. Okay, so now that we kind of understand the concept, let's actually go through some code for this. And so looking at the code for this, and if you want to pause here and take a quick break, this might be a good time to do that. But we're going to dig in and look at the code for this. So if you want to pause, I'll hold on for just a second here before we move on into looking at the actual code. But what we're going to do is we're going to code up this model. And notice it looks complicated when you look at it on the screen here, but really what we're doing, we're taking an input, multiplying by a weight, taking another input, multiplying by a weight, add those together, add a bias to it. That gives us Z. And if Z is 0 or greater, output a 1, which is red. Otherwise, output is 0. Not a whole lot of code there. Now, when we get that prediction at the end during training, though, we're going to say if it output a 0 and it should have been a 1, then that gives us an error. That could be positive or negative. In other words, we could get our truth could be blue when it should have been red, or our truth could have been red when it should have been blue, or it could be blue with blue or red with red, which will make our error 0. And in the cases where our error was 0, we're kind of saying, let's leave that alone. In other words, our error becomes, don't touch it if it's not, in other words, don't fix it if it's not broken. Leave it alone if we did get an error of 0. But when we get an error that's either in the positive or negative direction, then we're turning the knob one way or the other way for each of these knobs. Do more of that in this way or this way to move us away from or towards the right solution and away from what did the bad thing, essentially. Okay, that's probably enough time. So let's go ahead and start looking at the code for this. So we're going to code this up using object-oriented programming. So we're going to make a Perceptron class for this. And I'm just going to go through the slides for this, and then we're going to code this up based on what we learned from the slides, and then see it do something here in a little bit. Or maybe we'll go through the slides and I'll just bring the code up and we'll run it to save ourselves the time of having to type it all up and you watch me type. But let's go ahead and look at the Perceptron class framework first. So here's my Perceptron class. You'll notice the first thing about this is that I do have those two weights, weight 1 and weight 2. And notice I did set them to a random number. And the random number I picked was a random weight between -1 and 1. So it could be 0, could be -1, could be 1, could be anywhere in between. Random.uniform gives us kind of uniform distribution, just a randomly chosen number anywhere between -1 and 1. And I do that for both weights and the bias. So I've noticed that I didn't intelligently pick any of that. I just say randomly, let's just pick some values for this to start out our neuron weights at these. I also set the learning rate. I notice I have in my constructor the ability to pass that in as an argument. In my case, I have a default value of 0.1. So in other words, think about that as a percentage. We're moving the knobs by 10% of the error each time. And if we have a negative error, it's 10% in the negative direction. If it's a positive error, 10% in the positive direction. If we wanted to make slower adjustments, we could have a lower error rate. If we want to make faster adjustments, we could have a higher error rate. But do keep in mind that if we go too fast, we could overshoot and never find a solution or never have it trained properly. If we go too low, it could take a really long time with a whole lot of data for us to get kind of like a Loki who is kind of untrainable. A very stubborn perceptron in that case. Now so that's all of those are in our constructor. Python's constructor is that underscore init underscore. And notice those all become attributes: self.w1, self.w2, self.bias, and self. Instead of writing out all of learning rate, I just did self.lr for learning rate. Now, right now, the other three methods I have in this class, I just put stubs in there right now. I put predict. And what predict does is we pass in an X and a Y, and it's going to make its guess as to whether it was red or blue. In other words, this is where that calculation that we had back here is going to happen. It's going to output either a 1 or a 0 as its prediction. We're going to pass in an X and a Y, and it's either going to return 1 for red or 0 for blue. That's predict. We'll write the code for that here in just a second. Now, train, what train is going to do is we're going to pass it a bunch of data, and that data is already going to be annotated with the correct classification, red or blue, and an X and a Y coordinate that goes with that. And then we also notice I have the number of epochs. That's how many times I repeatedly go through the training process with that list of data. So we're going to pass in a whole list of data points that have an X and a Y, and then what the correct classification, red or blue output it should be. And it's going to run through all of that data epochs number of times. So it's just going to repeatedly train, in this case, the default 20 times on that training data. Now what test does the same thing that train does, but it's not training the system. It's just saying, did it get these data points right? Did it classify them correctly? Not making tweaks or adjustments to any of the thing. We're just testing it. All right. So now let's go into those individual methods. Let's look at the predict method. And notice this does exactly what we said that function should do. We pass in an X and a Y. What do? We take X, multiply it by weight 1, take Y, multiply it by weight 2, put that in Z sum, that local variable Z underscore sum. And then I take Z sum and I add the bias to that, Z sum plus equal bias, self.bias. And now I have my activation function. And my activation function just says if Z sum is bigger than or equal to 0, return a 1, which would be red. Otherwise, return 0. So this is just exactly what we had in our diagram in our predict function. That's either we're feeding in an X and a Y, it's outputting a 1 or 0. And how does it get those 1s or 0s? Just by multiplying the weights times the inputs and adding the bias and then running that through that active simple threshold activation function. Now, the train method is a little bit longer, but what we're doing here is the first thing is notice that outside for loop. And I've got comments in here that'll help you understand what's happening. But that for epoch in range epochs, that just says go through 20 times by default, or however many times we told it to train. And then I'm now looping over each of the items in the data list. And the data list itself has an X, a Y, and then a truth label. Is it red or is it blue? And so then notice I call self.predict, passing the X and the Y. That is happening right here. And I'm getting what the model predicted. I am then computing my error by saying take the label, the truth data that was passed into this, that was the data was labeled with, subtract the prediction from that. That gives me my error. In other words, if I guessed correctly, if it predicted right, the error will be 0. If it guessed wrong, the error will be either -1 or 1 in this case. And then what I do, here's the part where the knobs get adjusted. I take the error, I multiply it times the learning rate, and then I'm taking the X value and I'm multiplying it by that and adjusting my weight by that amount. In other words, that's where I'm turning the knob a little bit to adjust this weight. And notice that if the error rate is negative, this whole term is going to end up being negative. And I'm going to turn this knob in the kind of the opposite direction. If it's positive, I'm going to turn it in the positive direction. So this knob can either get turned up or down, even though this is a plus equal. I'm doing that for both of these. Both weights can be adjusted. And you'll notice that I don't just do learning rate times error, because that would be the same. We multiply it times the actual X or Y, because these can also be positive or negative. And that's what sets the kind of directionality. In other words, if this was negative and we had a negative error, then we're going to go in the positive direction. If this was positive and we have a negative error, we're going to go in the negative direction. So we're moving the opposite way of the direction that caused the problem. We're kind of trying to undo the problem in this case. And then we also move the bias by learning rate times error, which can also be positive or negative. So we're either moving the bias up or down a little bit. And then notice here I have this total error variable. That's just so as this runs, I can print out what the total error was after each epoch, so we can kind of see it as it runs. That's not necessary for this thing to train or learn. That's just for us to inspect what's happening. So I'm printing out, hey, after epoch 1, here's how many things were wrong. Epoch 2, here's how many things were wrong, and so forth. So you can see it improving as it trains. Or maybe not, depending on how we had things pan out. Now at the bottom of this for loop, I say, hey, if I ever get to a total error of 0, that means it perfectly was able to learn to separate these points in the training set. So there's no reason to continue to go through more epochs. It's like if your dog learned how to shake every time and it does it perfectly, let's stop sending them to training camp and now they have learned that. So that's what we're doing down here. We're saying, if my total error, I went through all of the training data and it got every one of them right with no errors, then we're going to break out of the loop and say, we got it. It learned. No reason it can keep going on if it got it. Now, last thing here is test. And you notice the test method and the train method are almost identical, except the part that adjusts the weights and the bias is gone. In other words, this part here, self.w1, w2, and bias, this whole part here, that goes away. We're still checking the data against the prediction, seeing if it's an error. And at the bottom here, we're just producing the results. Now, what the reason for this is after we've trained our model, we want to see how well it does with new data that it hasn't seen before without it continuing to make adjustments. That's what this does. It does the same thing, but doesn't adjust those weights anymore. We also could have done that by calling this again and setting the learning rate to 0, or making this so that it has an if statement that says train. I thought it was cleaner to just make a separate thing that's the train method and the test method. A little bit of wet code, but not too bad. Now, making some data to give this to try this, I've just made a function that generates a list of data and returns it. So let's quickly walk through that. Make an empty list. In this case, I'm making by default 20 training points. We're going to override that later on, but this makes 20 training or 20 data points. And what do? I basically create a random x and a y value. And then my truth function in this case, if y is less than x, I set that point to blue. Otherwise, I set it to red. Now we could change this function, truth function here, if we wanted a different kind of red versus blue. We'll see that here in a second. But then after I've generated that truth label for this x and y, I make a tuple of that. I drop it into my data list. And after I've made n of those, I return that list. Okay, now this, I don't want to spend a whole lot of time looking at this, but this is just the function that graphs the results so we can see them, red points and blue points on a nice two-dimensional graph. This is using a library called matplotlib. And essentially the way this works is matplotlib's a little clunky in that you have to have like the x points and the y, or x coordinates and y coordinates in separate lists. So I make the red list x and y, the blue list x and y, and the yellow ones are ones that it got wrong. And so I make those three lists. I run the code. If the prediction was equal to the label and the label was 1, those are red. In other words, this is where it got it right. When it got it right and the label was 1, those are red. Otherwise, they're blue. And if it got it wrong, I make those yellow. So this just fills up these lists with the red XY coordinates, the blue XY coordinates, and the yellow ones where it got the guess wrong. And then I do a plot. I do a scatter plot of those points. The red ones in red, the blue ones in blue, and the yellow ones in yellow. And then I do this plot.show at the bottom to show that two-dimensional plot. Again, this is a little clunky just because of how matplotlib works. But it does give us the desired result, which we'll see on the next slide. Now, let's go ahead and, instead of me running this live, let's just look at what the output would be. So here's what the output of that would be with this main program. So my main program for this one, I generated 300 training data points and then 300 novel test data points that it never saw before. So in other words, the training data is completely different data than the test data. And you'll notice here, I make an instance of my Perceptron. I kept my learning rate at 0.1. I then do a perceptron.test. I test it before I train it here. That's interesting because I want to see how well does it do with just its random garbage weights. And you'll notice in down in the bottom down here, my results, if I just, before training, it got about 50-50, which is kind of what you'd expect. It's kind of like it got some right and some wrong, and it was just kind of 147 out of 300 of them it got right. Not very good. Now, the next thing that I did is I now train it, and I do 100 epochs of 300 data points, and so it just starts going through. And what you'll notice is after epoch 1, it only got 37 of them wrong. So it went from getting over or 153 of them wrong with just one training round. Now it was down to only getting 37 of them wrong. And then from there, it did another training round and went from 37 down to only 9 of them wrong. And then it went again and now crept back up by 1, but then it went down to 8 and it got stuck there for a while. And then it went up to 12 and then 10 and then down to 4 and 2. And then finally at epoch number 77, it got complete perfect separation on the test data or the training data. And then when I ran it on the test data, it got 299 out of 300 of them. And that's points that it had never even seen before. So it was definitely learning the pattern. It was learning where red points are and where blue points are, not by memorizing them individually, but it learned the general trend of it. In other words, if I were to give this a point on this chart somewhere, like up here, it would definitely say red. If I get one down here, it would say red. If I get one down here, in the bottom right or this corner, it would say blue. And even ones that are really close to the dividing line, it's getting right. In fact, the only one that it missed was this yellow one right there. That's probably like right on the dividing line. It's so close to the dividing line that it couldn't quite figure that one out. It couldn't learn that one. But maybe with more training points, maybe with more epochs, maybe it could learn to do that one right too. Now, it's kind of fascinating that we didn't teach it the function. It figured it out on its own just by us training it. In fact, we could have test data that we don't even know what the function is. We could have points that come in from some scientific process and say, hey, these got this result. These got this result. You figure out how to decipher which ones are which. And it could do that. We're not telling it which one's which. In code, it's learning it on its own. And you can see that on our main program. Nowhere here did we tell it to do anything other than we made training data, we trained it, and then we tested it on brand new data, and look how good a job it did. Now, with neural systems like this, it's all about how we go about training them. The Perceptron starts out with random garbage values, and it did 50-50. It didn't know what it was doing. But very quickly, it started to, even after just one training round, let's go back to that a second. Even after one training round, it went from missing 153 down to only missing 37, and then another training round was down to missing only 9. So it's very quickly kind of converges on improvement. Now, the interesting thing about this is we're training it. We're not programming it. And we also don't even ourselves need to know what that function is. It'll still figure out how to classify those. We can just give it points and train it, and it'll learn which category which thing goes in. Kind of like you could show a person things like, hey, here's this is cats, this is dogs. Show them enough pictures and say cat, dog, cat, dog. They'll eventually learn what a cat is and what a dog is. And when one of my kids was a very young toddler, I remember I was out in front of my building here on the sidewalk, and there's a large ant crawling across, and I think it was my youngest, Riley. He crouches down and looks at it, and he's like, oh, kitty cat. Because to him, a cat was a thing with little legs that crawls around, and he hadn't seen ants before and didn't know what they were. So he thought the little tiny ant was a little tiny kitty cat, because that's his mind had been trained to think things that crawl around on legs, little animals, that's cats. And so again, it's all about the training. It's about what data we give it, what labels we put on that data, and how much data we give it, and how good a job we do at training it. Now let's look at a couple other examples here. So we looked at this one, we'll call that example 1. And that was if y is less than x, then blue, else red. And I've kind of up here in this upper left corner, that's where I'm putting the truth function that we're using. And again, you can see how well it did. It got all of them but one on novel data it had never seen before. Now let's change the function. Here's y is less than x divided by 2. So we changed the function. So now the line, instead of being kind of that perfect dividing line in the middle, it's different. It's kind of flat. Instead of being like, well, like this, now it's like this. And you'll notice that it actually converged after only 6 epochs. It got perfect separation, and it got all of them but 2 when it did the novel data it had never seen before. And you can see the 2 that it missed. They are right along the line. Yellow here, yellow there. So again, notice it went from missing 160. After one epoch, it only missed 22. And then it went 6, and then it got kind of stuck on 2 for a little while. But over time, the relentless pressure of when it makes mistakes on those 2, it would turn the knob a little bit, and then we would eventually end up with it tuning it so well on the training data we perfectly divided them. All right, let's look at another one. Example 3. This is just y less than 0. In other words, if y is below 0 on the y-axis, it's going to be blue. If it's above that, it's going to be red. And notice it went from missing, 143 of them to 29 to 2. And then it kind of jumped back up a little bit. In other words, when you see it jump back up, it's kind of means it overcorrected one of the knobs. But then you'll notice we very quickly then got stuck at 8, went down to 1, got to 0. And then we did the new data it had never seen before. It got 297 out of 300. In other words, 99% of them. Okay, example 4. X less than 0. X less than 0 is blue, else red. So looking over there on our chart, it converged after 16 epochs. And we got all of them but 3. So again, 99% of them are correct again. And again, if we had more training data, we could probably get this to do even better than this. But this is still really, really pretty good. Look at how good a job it did over there. Okay, now, you might at this point be thinking like, wow, this is the simplest kind of perceptron we can have. And it's learning to sort out these points by just us training it. We're just showing it data and it's figuring it out on its own. It's kind of remarkable in a way that it's able to do this. But it is important to note that they do have limitations. And those limitations look like this. So notice I changed my function around. I said if y is less than negative 0.5 or it's greater than 0.5, then blue, else red. And you'll notice, look at how many it missed with this. It got some right in blue and some right in red, but all of those yellow ones that were wrong. In fact, after training, it did actually worse than it did before we did any training. It was about 50-50 when it started. And then at the end, after training, we only got 126 out of 300 rather than 137 out of 300. Now, why is that? Well, the problem with this is the kind of problem that with just 3 knobs and 1 perceptron, we can't really tune, because you'll notice that Y, it has to give us blue both when Y is up here and down there. So when we're changing the weight of the blue knob, we're going to keep fighting with it, trying to put the ones at the bottom in blue, but then the ones at the top in blue, and then the ones at the bottom in blue, and then the ones at the top in blue. We're kind of, every time we're hurting something that we've tried to fix. So it's kind of like the knob keeps moving back and forth between two things that we can never find a point that will satisfy both of those, because we don't have enough knobs or enough weights to do that. So it's kind of like trying to turn a knob in a way that will satisfy two things that cannot be satisfied with that one knob. Or in this case, 3. And you can see that. Look how poorly it did over there. Now let's look at another one that it fails on. Here's another one. Y is less than x divided by y. So this is a nonlinear function. And it does a little bit better than the kind of piecewise defined one we had over here, but still pretty bad. Look at all the yellow points over there of things that it got wrong. Again, it's fighting with itself. And you can see that. Let's go back and look at this. You'll notice that 118, and then 115, 116, 108, 122, 115, 120, it keeps it's kind of finding a middle ground where it's doing the best it can, somewhere around 120. But that was really kind of, or the error, that's the minimum, that was the best it could do. It was not able to do any better than that after that. So terrible results from this. And so this isn't really a problem with the perceptron as much as we're trying to have it solve a kind of problem that it can't solve. So why did those two fail so badly? The answer is that a perceptron this simple doesn't have enough that we can do with it based on the feedback to satisfy conflicting things. In other words, we have this piecewise defined thing at the top with y has to be less than 0.5, but also greater than 0.5. And we have a knob that's either going to move it one way or the other. We can't satisfy both. Making it better for one is going to make it worse for the other, and vice versa. And then the bottom one is nonlinear. So turning that and trying to find a dividing line between those 2 points, we're not going to find it because it's a nonlinear dividing line. It would have to be parabolic or a curve of some sort to separate those. And we can't do that because all we have are this line that's separating them that we're making adjustments to. Bias moving the line up and down, the two weights kind of adjusting to the slope and the offset of that. We just don't have enough controls to be able to improve the error any more than we have. Now, that brings us to the limitations of this simple perceptron like this. And the first limitation is that are illustrated by this, is that we need a single perceptron can only handle things that are linearly separable. In other words, if we can separate the data points by a straight line, then a perceptron can figure that out and be trained to do that. But if the data requires a curve or a more complex boundary, like a points inside a circle versus outside the circle, the perceptron's going to fail because turning the knob to improve one point is going to hurt it with respect to other points. We don't have enough that we can make adjustments to have it satisfy multiple things simultaneously. It also, another limitation of perceptrons is when we're dealing with something like that step function as an output or that threshold, we can only deal with binary classification because it only has that single output, and it's either going to be a 0 or a 1. In other words, dividing things into red or blue in our case. Now, you can, by changing the way our step function works, or our threshold function, or activation function, I should call it, you can handle other more, or I'll say more categories of things, but they have to be along a linear boundary. And we're going to see that next class in the lab we do coming up. Now, all right, so rewinding back to, we had this limitation of a single perceptron. What if we want to do something more complicated? Well, that's where we get back to this concept of a network. By adding neurons together in groups, we can get around that simplicity of just having too few knobs to do complex things. So with something like this, neurons feeding other neurons feeding other neurons, we can now have something that can now solve nonlinear things. So we found that just like a single neuron has limited functionality, but can do stuff, can learn, and can solve problems just by teaching them things. Single perceptrons also have limited functionality. And if we want something that's more complex, we just need to make groups of those things together. So what we're going to do coming up, not next class, but the class after, is we're going to start looking at connecting more than one perceptron together to make a group of them. And this is where we get from, rather than a single neuron to a neural network, is using them together to work as kind of a team to solve more complex problems. So more knobs to play with, more things that we can do, more interconnection between those things, the more we can do. So what's interesting is that what's the limit of the complexity of what you can do with neural networks by just adding more and more nodes and connecting more and more together? Well, can that solve more complex problems? Obviously, the answer is yes, because your neural network in your brain is reading or listening and understanding what I'm saying or what you're looking at on the screen right now. And so by adding a large number of neurons connecting together in a large network, we can start doing really complex things that ultimately, at the end of the day, can end in, like humans, general intelligence. Now, going forward, we're going to have this model of imagine each of those things in the middle there that's kind of stripped down the middle. Those are our perceptrons. The things on the left are input nodes. The things on the right are output nodes. So we're going to kind of wire up these networks of neurons that have inputs that connect to multiple of these that then connect to multiple outputs in order to do things. Now, a little bit of terminology. That on the left is called our input layer. Those are nodes on the left are input layer nodes. The ones in the right are output. That's separate nodes as well. And then in the middle, that's called our hidden layer nodes. And it turns out in neural networks, you might have more than one hidden layer. It could be many layers, kind of like how the human brain has neurons that connect to neurons that connect to neurons, or this example we had back here. Notice I've got several layers deep of that going across in that. And this says next class, but we're actually going to do a lab with a single perceptron. And it's going to be 2 classes from now. We're going to look at writing code with actual neural networks with more than just one perceptron. Next class, I want to do a lab where we're going to do a single perceptron, but eventually we're going to get to a lot of layers, hidden layers, a lot of inputs, a lot of outputs, and we're going to train these things by adjusting the weights and the biases of all of these nodes through a training process to solve complex problems, not just which points are red and which are blue on a linear test, but we could get these to solve the kinds of things that you would be hard pressed to get a computer to solve. Like, is this picture a picture of a cat or a dog, or what kind of data is this that I'm looking at in this data set? Is this data from somebody's cell phone that shows them walking or running? Or there's a whole bunch of things that we can do with these neural networks, or computer vision kinds of things. What am I looking at in this? And these neural networks, if you make them large enough and train them enough, then you can do remarkable things. And these are at the heart of large language models and a lot of other things that we're going to see throughout the semester. So next class, though, before we get into large networks of those, I want to spend a little bit of time focusing on what can we do with a single neuron or a single perceptron. So next class, we're going to have a lab where we're going to get our hands into some code. We did a little bit of code today. I presented it. We looked at it. Next time, we're actually going to throw some of that code together and write some stuff. But we're going to have a single perceptron that, rather than just doing something that's passive, like sorting points into red and blue groups, that's doing something, but I want something that's kind of dynamic that we can actually see. So next class, we're going to take a single perceptron, a very simple single neuron. We're going to put it into kind of a simulated environment and have it be the brain that drives a robot and see if it can learn to drive that robot. So that's going to be pretty fun. And you guys are going to get to experiment with that and play with that and have your first lab. Okay, so we'll stop there. And next class, we're going to dig into that lab. You'll get to write some code. You'll have your assignment to do that. Do remember to keep looking at the course site for those little check-in assignments that show up. They're like little quizzes. Make sure to look for those. It's important to keep up with those. And then also next class, be ready for that first kind of lab assignment because you're going to get to write some code. And if you want to play with the code that I have posted in these slides, you can get that from the slides, or I can post it to the course page under the resources section. I can post a little thing so you can play around with changing the number of epochs, change the function, change the training data, more training data, less training data. It's actually pretty fun to experiment with, so I'll post that to the course page as well. Okay, let's stop there, and everybody stay safe, and I'll see you next time, and we're going to get our hands dirty and write some code and have some fun giving a robot the simplest brain you can get, just about the simplest brain you could give it, and see if it can learn to do something for us. So that should be fun, and it'll be kind of surprising to me as well. We'll see how it goes. All right, see you next time.